Oh, thanks for the kind introduction, and thanks to the organizers for this workshop. So I'm going to talk about my recent work on correlation clustering, joint with Soheil Behnezhad, Moses Charikar, and Weiyun. So let me start by defining the problem of correlation clustering. So we are given an input graph G on n vertices, where each adjacent pair of vertices is considered similar, and each non-adjacent pair of vertices is considered dissimilar. And the goal is to partition the vertices into arbitrarily many clusters, so that we want the pair of vertices in the same clusters to be similar and pairs in different clusters to be dissimilar. And formally, we want to minimize the total number of mistakes that we make, whereby a mistake, we mean a similar pair that goes across different clusters, or a dissimilar pair that lies in the same cluster. So let's look at some examples. If the input graph is a disjoint set of cliques, for example, then there's a perfect clustering with no mistakes at all. And for this second example, and let's look at this particular clustering. As we can see, it makes a total of 4 mistakes. And it turns out this clustering is actually an optimal one for this example graph. So what do we know about correlation clustering? It's APX hard. And then what about the approximations? So there's this LP rounding based algorithm, which achieves an approximation factor of 2.06 by the work of Chawla, Makarishev, Shrum, and Yaroslavtsev. And this is very recently improved to 1.994 by the work of Cohen, Adad, Lee, and Newman. And they achieved this by strengthening the LP using a technique called Shirley-Adams hierarchy. And on the other hand, there's a extremely simple 3 approximation for correlation clustering, which is called the PIVOT algorithm. And this is by the work of Allen, Charikar, and Newman. This PIVOT algorithm remains as the best known approximation so far by any combinatorial algorithms. And it is also crucially used in the above mentioned LP-based algorithms. So how does the PIVOT algorithm work? First we pick a uniformly random vertex as a pivot. And we pick a uniformly random vertex V as pivot, and we put V all together with all its neighbors inside a cluster. And we remove this cluster from the graph and recurse on the remaining graph. So let's finish this process on this example graph. Next, we have this pivot, and we cluster it together with all its remaining neighbors, and we get this cluster. We remove it, and we continue. And this will be the final clustering that we get from the PIVOT algorithm. And we know that the expected cost of pivot is at most 3 times the optimal cost. But the downside is that this algorithm is highly sequential because we only pick 1 pivot in each round. So it may take as many as O of n rounds for certain graphs. So this raises a natural question, which is, can we get a good approximation in few rounds, and preferably in constant many rounds? And this question has led to a rich literature on obtaining good approximation for correlation clustering in few rounds. And here's a table that summarizes some of the previous work in in the large-scale data models of sublinear massively parallel computation, semi-streaming model, and also distributed local model. So at the top of this table, we have the pivot algorithm, and it's followed by this first line of work that focuses on parallelizing the pivot algorithm. So this line of work, in this line of work, the three they all maintain the almost three approximation guarantee, but those algorithms do run in super constant many rounds. And on the other hand, there is another more recent line of work, which focuses on designing constant round algorithms for correlation clustering, but at the cost of having a larger approximation. And in this work, we achieve the best of both worlds. And we give almost three approximation algorithm that runs in essentially constant many rounds. So let me dig a bit deeper into those two lines of works. And let me start by talking a little bit about the second line of work, which is based on this technique called clique decompositions. And this consists of the work of Cohen-Haddad, Latanze, Mitrovic, Rosifard, Parasides, Notarsky, and the work of Asadi and Wang. So the key insight here is that to get a constant factor approximation, it suffices to find clusters that are either near cliques or singletons. So for example, for this particular input graph, an output clustering may look like this. There are two perfect cliques at the top. And if you look at this pretty dense subgraph at the bottom, turns out this subgraph is pretty dense, but it's still not dense enough to be considered as a near clique. So this approach will actually cluster those vertices as singletons. And it's shown that such clusters can be found in constant many rounds. However, the downside of this approach is that the approximation constant here seems to be inherently large. So for example, if we consider the 1 minus epsilon cliques, which roughly means that each vertex in a cluster is connected to at least 1 minus epsilon fraction of the vertices in that cluster, then the approximation is at least roughly 1 over epsilon squared, very roughly speaking. And now let me turn to the first line of work that focuses on parallelizing the pivot algorithm. And I will focus on a particular variant of the parallel version of pivot, which I will call the parallel pivot algorithm. And let's compare it, the output clustering of parallel pivot with the original pivot algorithm. So for the sake of this comparison, it would be very convenient to consider the following alternative view of pivot. So instead of recursively mark a random vertex as a pivot, we first draw a uniform random permutation on all the vertices. And then in each round, we mark the vertex with the minimum rank as the pivot, and we remove it together with all its neighbors, and we recurse. And in this way, this is the final output clustering we get. And now let's look at how parallel pivot algorithm works on the same input graph and the same permutation. The main difference here is that now in each round, it picks multiple pivots, namely all the vertices that are that have local minimum rank in the current graph. So for example, in this example, in the first round, the vertices 1, 6, and 8 here will be the pivots. And we remove all of them together with all their neighbors. And then in the second round, the only vertex that's a local minimum is this vertex 3. So we mark it as a pivot and we remove it together with its only remaining neighbor 4. And we continue this process in the next round. This vertex 5 is marked as a pivot and we remove it together with its neighbors. And this will be the final output of parallel pivot. So the first observation about parallel pivot is that it outputs the exact same clustering as pivot. Oh, sorry. So I forgot to mention that after we, in parallel pivot, after we have found all the pivots as in the pivot algorithm, for each non-pivot vertex, it will join the cluster of a pivot neighbor of minimum rank among all the neighbors of the non-pivot vertex. So in this way, the parallel pivot algorithm will output exactly the same clustering as pivot. However, because now there are dependencies across different rounds, pinning down the round complexity of parallel pivot is a slightly more complicated task. And in the work of Blalock, Feynman, and Schwen, they show that the parallel pivot algorithm terminates in O of log n square rounds with high probability. And this is then settled to the tight bound of theta log n rounds by the work of Fisher and Novi.
Question?
Yes.
So, okay, I don't remember the details of this algorithm, but I remember seeing an algorithm before, like that was called star contraction when I learned it, where like everybody flips a coin and you're the center of your star, or you are looking to be attached to the center of a star. And then every day, if I'm looking to be attached, I look at all my neighbors, and if any of them is a center, I attach myself to them. Is this like, this sounds like a very similar algorithm, and I don't remember at all what the bounds on star contraction were, how many rounds it takes to terminate. But is that similar? Is it like a similar analysis?
I'm actually not sure about the exact algorithm that you're talking about, but there do exist like different versions of the parallel implementation of the pivot algorithm. So for example, there's this so there's this for example, there's this 3 plus epsilon approximation where the key insight there is that in each iteration, for every vertex has equal chance of being marked as a pivot. So if you can maintain some guarantee like that, then I think it's possible to bound the number of rounds by polylog n, say like log n squared or something like that. So hope that answers your question. So yeah, let me continue. So another observation about the parallel pivot algorithm is that so actually for both pivot and parallel pivot, the set of pivots that are found forms a maximal independent set. And there are no lower bounds for finding a maximal independent set in different large-scale data models. So for example, there's this lower bound of omega root log n over log n rounds in the local model. And there's also a conditional lower bound of omega log n rounds in the sublinear MPC model. So this suggests that if we want to design constant round approximation for correlation clustering, then it's not a good idea to use all the pivots that are found by the original pivot algorithm. So this idea actually inspires our R-pivot algorithm, which is a truncated version of the parallel pivot. And the key intuition here is that we only run the parallel pivot algorithm for R rounds, and we will only use the pivots found in the first R rounds. And after that, each non-pivot vertex chooses to join the cluster of its pivot only if that pivot has been discovered within the first R rounds. Otherwise, it will form a singleton cluster. So for example, if we run our R pivot algorithm with R equals 1, we just run it for one round on this graph. As before, the vertices 1, 6, and 8 will be the pivots. And this will be turns out be the final output clustering for this algorithm. And if we run our pivot for one more round, then in round 2, we'll mark this vertex 3 as pivot, and this will be the final output clustering. So now let me formally describe our R-pivot algorithm. It works as follows. So we first draw a uniformly random permutation on the vertices, and we proceed as in parallel pivot for R rounds, and we find a set of pivots. And after this, every pivot will start its own cluster. And in this last step, every non-pivot U will join a pivot neighbor V if V has minimum rank among all the pivots and unsettled vertices in the neighborhood of U. And if no such V exists, U itself will form a singleton cluster. So this last step is a little bit dense. So let me explain it a little bit more here. So for example, in this graph, if we look at, if we run the R-pivot algorithm for one round and look at this vertex 7, it has a pivot neighbor 6, but it doesn't choose to join that cluster. And that's because this vertex 7 has another unsettled neighbor 4 with smaller rank than 6. And similarly, this non-pivot vertex 11 doesn't join the cluster of 8 because it has another neighbor 3 that has smaller rank. And this vertex 3 is not settled in the first round, in the sense that it itself is not a pivot and it's not connected to any pivot found in the first round. However, if we run our pivot for another round, we can see that now 7 will join the cluster of 6 and 11 will join the cluster of 3. Because now both vertices 3 and 4 are settled in the second round. And in particular for this vertex 11, it chooses to join the smaller, the pivot neighbor 3 with smaller rank. So the reason we want this last step is that it actually makes sure that each cluster output by R pivot completely lies inside some cluster output by pivot. So if we compare for example, if we compare the output clusterings of both pivot and R pivot for this input graph, we can see that indeed the output clustering of R pivot is a refinement of that of pivot. So also this means that like every extra mistake we make for in R pivot will be an edge that lies inside some cluster output by pivot, but now go across different clusters in the R-pivot algorithm. And here are some additional examples. So if, again, the input graph is a disjoint set of cliques, then no matter how the ranks of vertices look like, the output clustering of both R-pivot and pivot will be the same. But now if we look at this particular graph, where we have a large clique, and with path attached to one of its vertices, and let's fix this particular permutation of the vertices, and we can see that this is the output of the pivot. It will produce 3 clusters, and the number of mistakes it makes is 2. On the other hand, if we run our R-pivot algorithm for 2 rounds, then the only pivots that are discovered will be this vertex 1 and this vertex 3. This means that all the vertices that are in this large clique will be singletons in the output of R-pivot. So we might be worried that this is actually this looks like problematic, because we are now like paying for every edge inside this large clique. But this is actually okay, because this event actually happens with low probability. So on average, we're still good. So I want to pause here a bit and see if there are any questions.
Sorry, can I ask a question?
Yeah.
At a high level, like all of this talk about cliques is making me think about the densest subgraph problem. Would you comment like how similar the correlation clustering problem is to, or dissimilar to, the densest subgraph problem?
In the densest subgraph problem, the goal is to find one densest subgraph. But I think maybe like, because like this example, there's only like one large cliques, but there are so I feel like maybe if we look at the approach through the clique decomposition, then maybe an instance that's easy for the densest subgraph problem will coincide with like the good instance for correlation clustering. But I'm not sure about if there are any concrete connections between those 2 problems.
Sorry for asking a weird question.
No, it's a very good question. I just don't know like about a concrete connection between the 2 problems. So good. Let me continue. So let's turn to the analysis of the R-pivot algorithm. It's not hard to see that by design, the R-pivot algorithm runs in all of our rounds. But what about the approximation factor? So our main theorem says that the expected cost of our pivot algorithm is at most the cost of pivot plus an extra cost that is 1 over that is in the order of 1 over R times the optimal cost. since we know that the pivot algorithm is a 3 approximation, this implies the R pivot algorithm is a 3 plus O of 1 over R approximation. And this has several direct consequences. So namely, if we just implement, we can implement the R pivot algorithm in several large-scale data models, and then we can obtain a 3 plus epsilon approximation for correlation clustering. For example, we can do this in O of 1 over epsilon rounds in the sublinear MPC regime. And for example, in O of 1 over epsilon passes in the streaming setting with linear space, and in O of 1 over epsilon rounds in the local model and the congest model. And we also have a delta to the O of 1 over epsilon time LCA, where delta is the maximum degree in the graph. And I also want to mention one point, which is that so the approximation guarantee here is actually instance-wise, which means that our R pivot algorithm approximates pivot well on all graphs, not just the worst case graphs. So for example, if there are some input distributions where the pivot actually does better than 3 approximations, say it achieves an alpha approximation on some input distributions, then our R pivot also has the corresponding alpha, almost alpha approximation guarantee on the same input distribution. So how do we prove this approximation factor? We will look at the set of extra mistakes made by the R pivot algorithm as compared to the pivot algorithm. And it's clear that the cost of R pivot is the most that of pivot plus the size of this extra set of mistakes. So the goal now becomes showing that the expected cost, the expected size of X is in the order of opt over R. So back to this example, the set of mistakes are precisely those edges marked in red double lines. And as we observed earlier that the output clustering of R pivot refined set of the pivot, all these edges are precisely those that lie inside the same cluster of pivot, but now go across different clusters in the output of R pivot. So how do we bound the size of X? We use the standard framework of charging the mistakes to bad triangles, where a bad triangle is a triplet of vertices where exactly 2 pairs are adjacent. And bad triangles is very useful because any clustering must make at least one mistake on any bad triangle. So if, for example, here, a clustering that put all these 3 vertices together inside the same cluster will give a cost of 1 for this red non-edge. And for this clustering of 3 producing 3 singletons, we pay a cost of 2 for the 2 red edges. And for this last clustering, for example, we pay for this red edge that go across the 2 clusters. So one thing is that if there exists k edge disjoint bad triangles in the graph, then this gives a lower bound of opt. And in the original analysis of the pivot algorithm, it charges each mistake to a bad triangle locally. So for example, in this baby graph, for this non-edge mistake, the analysis will charge it to this bad triangle here, which consists of the two endpoints together with their common pivot neighbor. And if we look at this green mistake, then it will be charged to this particular bad triangle, which includes both endpoints and also the pivot neighbor of one of the non-pivot endpoint. So, however, such local charging schemes don't really work for analyzing our R-pivot algorithm. And the reason is simple. So here is a baby version of the example that we have seen earlier. If we want to charge for this mistake 6, 8, then there really are no like bad triangles locally. And in fact, there are no bad triangles at all inside this clique. So the key idea here is that we want to charge bad triangles that can be potentially far away from the mistake. So for example, roughly speaking, we would like to charge this mistake 6, 8 to potentially a bad triangle that's far away. And in this case, we will charge it to this bad triangle at the end of this path, consisting of the verses 1, 2, and 3. But how do we really find those bad triangles that are far away? To do this, we draw connection to sublinear-time algorithms. In particular, we will use the following recursive query process to identify the pivots. So let f pi of v indicate whether v is a pivot when we run the original pivot algorithm under permutation pi. And it's clear that v is a pivot if and only if none of its smaller rank neighbors are pivot. And this can be determined recursively. So for example, we wonder whether this vertex 7 here is a pivot or not. And it will recursively query this neighbor 5, which has smaller rank than 6. And 5 will continue to query its neighbor 1. And vertex 1 turns out to be a pivot because it has no other smaller rank pivot neighbors. So 5 knows that it's not a pivot. So 7 then turns to query the vertex 6. 6 queries 3, and 3 turns out to be a pivot. So 6 is not, and then we know 7 is a pivot. So this simple recursive process is studied extensively in the context of sublinear-time algorithms. And in particular, in this beautiful work of Yoshida, Yamamoto, and Ito, they show that for a random vertex v and random permutation, f pi of v can be determined in O of m over n recursive calls, where m is the number of edges in the graph. And for our purposes, we need to use an analog of this function f pi of v. So instead of starting from a single vertex, we now need to start from pairs of vertices, and namely, we need to start from we want to start from a pair that's a mistake in X. And in particular, we consider the stack of recursive calls that start at a given mistake in X. And we show that at some point, this stack will contain 2 R vertices. And we're also interested in the first moment that this stack contains a certain number of vertices for, say it contains L vertices. The first moment when the stack contains L vertices for some L that's no greater than 2R. And we show that the moment this happens, the last 3 vertices in the stack must form a bad triangle. So back to this example, we start the recursive query process from this mistake 6-8, and we recursively make queries along this path, and eventually we will find this bad triangle at the end of this path. And our main technical lemma says that for any pair of vertices, the expected number of charges to triangles involving both vertices is in the order of 1/R. And this is sufficient for showing that X has expected size of O of opt/R, which then in turn proves our main theorem. So let's see. So as a summary, in this talk I talk about our R-pivot algorithm, which is a 3 + epsilon approximation and runs in O of 1/epsilon many rounds. The approximation factor is close to a natural barrier of 3 for any combinatorial algorithm, and the round complexity we achieve here is essentially constant. There are several interesting open questions remaining. For example, it would be very interesting to get a better than 3 approximation in constant rounds, which will probably involve new techniques. It will be also very interesting to see if there are any lower bounds we can show for the correlation clustering problem. And finally, can we get any results for other big data settings where there's no clear notion of rounds? For example, can we get efficient algorithms with good approximations in the dynamic setting or in the sublinear-time algorithm setting, and so on? So that's the end of the talk. Thank you for listening.